Chemistry in a nutshell. So what is thermochemistry? Study of heat, to put it simply. So whether a water absorbs or loses energy, whether metal gains or loses energy, what a solution where you have a chemical dissolved in water gains or loses energy. These are all examples of thermochemistry. We're going to talk about each one in detail. Before we do that, first we have to first talk about how to calculate heat. Heat is represented by the symbol Q. And what you use is the MC triangle T form, also known as MCAT. Q equals MCAT. The M is your mass. It's your total mass. So if you have water by itself, it's just the mass of the water. If you have a metal by itself, it's just the mass of the metal. If you have a chemical, then what you really have to do is there's going to be what's called the mass of the chemical plus the mass of the water. And the reason for that is you can't directly measure a change in temperature for a chemical because it's a solid. It's impossible. So what we typically do, we do what's called create a solution. So solution is when you add a chemical to water. That's the most common solvent. There's other solvents, but for our purposes right now, we're going to call it chemical plus water. Your chemical is called your solute, and your water is called the solvent. So together, that's considered your solution. So when we do mass for a chemical in water, we call it the mass of solution. TF and T initial, that's your final temperature, it's your initial temperature. It's not big minus small number. Please don't make the mistake. T specific capacity, which is a constant, as you hopefully are aware, and that varies based on the substance. So we're going to try the first thing, which is the different variations of calculating heat. There's heat of water, which is called Q water. We have heat of metal, which is called Q metal. And we have the heat of a chemical in water, which is called Q chemical. The third one's going to be the most challenging because you have to do a little something at the end of it to get the right answer. But we'll talk about that. All right, so let's first talk about the heat of the water. So it's just water by itself. So either you're putting on a hot plate to make its temperature go up, or you're putting it in an ice bath or in a freezer to make its temperature go down. Those are your two options. What we want to do is calculate that heat. So it's calculated when water is gaining or losing heat due to something heating or cooling it. So here's an example of it. Calculating heat absorbed by 100 grams of water. So because it's water by itself, this is our mass. There's nothing else to add. Temperature, it's going from 30 to 50. So 30 represents our TI. 50 is TF, because that's our T initial, that's our final temperature. And this is our C, specific capacity is here, 4.18. So I'm going to write the formula down first. Q chemical is equal to MC triangle T. So we're going to plug and chug now. So it's 100 grams times 4.18. That's what you do mathematically. You're just going to multiply all three of these variables together. So 100 times 4.18. This change in temperature is 20 degrees Celsius. Subtracted, right? That's the math. So when you multiply all these together, you get 8360 joules. That represents the Q of the water. We refer to as this having a positive Q. And it kind of makes sense. If you look at it, in order for the water to go from 30 to 50, it had to have gained energy, right? So that's what's referred to as an endothermic reaction, which we'll talk about a little later. But your heat is positive because you're gaining heat to make your temperature go up. This is only when you have a metal by itself or when you have water by itself. So just keep that in mind. So let's talk about the second variation, which is the heat of a metal. So calculating when a metal is gaining or losing heat due to something adding heat to it or taking it away. So whether you put it over a flame, whether you put it in the fridge, whatever, there's two different ways you could have a heat exchange. So let's look at the calculation. Calculate heat absorbed by 100 grams of copper, so by itself, so this is going to be our mass again. Temperature increased from 30 to 50, so there's our initial, there's our final, so TI, T final. And there's specific capacity. Because the metal, it's going to have a very small value, which is what we expect it to be. So this is our C. Why isn't the C producing itself? There you go. All right, so now we're going to plug and chug at this point. So Q metal equals MC triangle T. Your mass is 100 grams. C capacity is 0.385. Change in temperature is 10, right? 30 minus 10. Sorry, 30 minus 20 is 10 degrees Celsius. So we multiply all these reading numbers together. And in case you're wondering about this whole unit thing, it's actually a form of making sure you set up correctly because your C should go away, right? C divided by C. is no C's anymore. They divided out. Grams divided by grams, those go out. So you're left with just joules, which is energy, and that's what you're shooting for. So the unit's there just to help you figure out if you set up correctly. So this is 770 joules. Notice how the same mass of metal as the earlier water requires so much less energy to raise its temperature by 10 degrees Celsius. This required 770. The other one requires 8360. Why the difference? Specific heat capacity. The lower the specific heat capacity, and this is a very important detail to remember. So the lower specific heat, HT, the greater the change in temperature. Whether it's up or down, it's just going to experience a greater change in temperature. It's going to lose heat the most. It's going to absorb heat the most. So in this situation, it absorbed the heat very well, so much so that it only took 770 joules to make it go up by 10 degrees, whereas the water required 8360, which is about, 9 to 10 times more energy. So that's an important detail to note. All right, and then the last scenario, calculating heat of a chemical. So in order to calculate, you dissolve the chemical in water and first solve for the heat of the water the chemical is dissolved in. So when you're doing the Q of the chemical, you have to do it indirectly. You can't directly measure the change in temperature of a chemical because it's too difficult. So what we do, we put in water, and what we're going to do is collect our data from the point of view of the water. So all this data is actually the Q of the water. So keep that in mind. So we're going to remember that the Q of the water is equal to negative Q of the chemical. This is a very important detail. What this tells us is that all we have to do at the end of our calculation, once we get our Q of the water, flip the sign, and that's going to be the Q of the chemical. That's all this is telling us. So the math is going to be very similar to what you saw for Q of the water. The only difference is at the end we've got to flip the sign. Why do you have to flip the sign? Because what you're doing is collecting data from the point of view of the water, right? The water gained energy. How did it gain energy? There was no heating source. It gained it from the chemical. When the chemical dissolved in water, it produced energy, and that's what you're calculating and measuring. But that's not what we want. We don't want to know what the water's doing. We want to know what the chemical is doing. So if the water is gaining energy, the chemical must be losing energy. And that's an important detail to keep in mind. So here's the difference in the calculation. This is going to be our mass, which is 80, plus 120, which is 200 grams. We've got to add the mass together. That's the one thing you haven't had to do until now. The temperature is still TI, TF. And the specific heat capacity, because we're doing the reaction in water's perspective, we use the 4.18 we used before. So anytime you're doing a chemical in water, your specific capacity is 4.18. Just remember that. So there's our formula as always. We write the formula first, then we plug and chug. So now we have 200 times 4.18 times 30 minus 20, which is 10. We multiply all this together, and we get 8360 again. Wow, there goes that number. But here's the thing. This is really our Q of water. Why? Because all this is from the point of view of the water. You measure the temperature of the water, specific capacity of the water. The only thing you did was add the mass of the chemical in water, but that's a moot point. What you need to remember here is that at the end of this, you got to flip the sign. So when you flip the signs, and they're going to be 8360 joules. And here's the thing. You see how the temperature went up in this situation? Okay, so remember how we said that your Q is positive or negative based on your absorbing energy or losing energy? So we're going to ignore the water altogether. We want to know what's going on from the chemical's point of view. From the chemical's point of view, it is losing 8360 joules, right? This is a negative Q, which means you are losing energy. So how will we verify it? Well, in order for this to happen, that means the temperature of the water must go up. So we're going to look for, whenever we have a solution, that's what's happening to temperature. Because the temperature increased, we're going to assume our Q is going to have to be negative, because there's no other way for the water to increase in temperature. We're going to talk about this whole relationship between Q, losing energy, once we talk about endo and exo in a second. So we'll come back to this idea. So here's some questions for you. What's the amount of heat released when 10 grams of ammonium chloride, so there's our mass, the chemical, but we need our total mass, right? So how do we get our total mass? Well, it's going to be the 40 plus the 10, which is going to be 50 grams. This is our TI, TF. Notice this time the temperature is decreasing. So you actually get a negative number out of this. What's specific capacity? Water. Because we said whenever you're doing chemical in water, that's what you're going to use. So we're going to talk about this one, and we'll talk about their two calculations underneath in a second. So for this one, your Q of water is equal to 50 grams. That's 4.18. 10 minus 30. This is negative 20. So your answer actually comes out as negative, right? But remember, what do we do at the end of all this? We flip the sign. So it's 41.8. Does it make sense? Yeah, it makes sense, because here's why. Water lost energy. Okay, where'd the energy go? To the chemical. So whenever you have a solution and your temperature goes down, you're going to assume that from the chemical's point of view, your Q will always be positive. So we'll talk about this on the next slide in more detail. This next question is, what is the heat of 50 grams of aluminum that is heated from 20 to 30? Notice the same mass for the metal as there was for the chemical and water together, just to show you the difference. Specific capacity of aluminum is 0.900. So same thing, we do Q the chemical, there's no adding here, right? Just 50 grams times 0.9 times 30 minus 20, which is 10 degrees. So 450, no flipping of the sign. Why? We only flip the sign when it's a chemical and water. That's the only time. Please remember that. So notice 450 joules is all you needed to make its temperature go down 10 degrees Celsius. In this situation, why is it going to be a positive number? Well, think about it. You're going from 20 to 30, you're gaining energy, right? So it's gaining energy from something. What doesn't matter. But from the point of view of the metal, which is our system, which we'll get back to in a second as well as system and surroundings, what that means, it's going to have a positive number. The third question, which would reach 100 degrees fast, 50 grams of aluminum or water? Well, it's opposite. Aluminum's lowest specific capacity. Because remember, what do we say? The lower specific capacity you have, the greater the change in temperature. All right, so now we're going to come back to describing chemical reactions. So we're going to identify system and surroundings. So system is where we want to focus our attention, which is usually the chemical. If you have water by itself, water is the system. If you have a metal by itself, the metal is the system. So it varies based on which of the three possible routes you're taking on the question. Typically, a chemical reaction. Surroundings is everything else, including the water when chemical dissolved in water. So surroundings, if it's water by itself, then it's everything around the water. If it's metal by itself, it's everything around the metal. If it's a solution where you have a chemical and water, that's where it gets really interesting, because now the chemical, let's say Na plus, Cl minus is your chemical, that's a system, so the water around it is actually the surroundings. And that's the part that becomes really interesting, because, you know, it's easy to assume that the water is part of the system. It's not. When we have a chemical and water, chemical is a system, water is a surrounding. That's the most important thing in all this, in our brain farts on this stuff. All right, calorimeter is where we usually do heat reactions to determine if it's exothermic or endothermic, whether we're producing energy or absorbing it. It's an insulated device like a coffee cup, and it's just used to calculate heat. That's pretty much its functionality. All right, so types of reaction. Depends completely on what your system is. Exothermic means exit of heat. So, what's an example of exothermic? Your water is cooling down. So, your temperature of your water goes from 50 degrees Celsius to 30 degrees Celsius. It lost energy, right? That's exothermic. It's losing energy. The other variation is endothermic. Endothermic is you're absorbing energy. So, what's an example? Your metal is going from 30 degrees Celsius to 60 degrees Celsius. It's absorbing energy. So entrance of heat. Exit, losing, so you see a decrease in temperature. Entrance, you're absorbing, so you see an increase in temperature. And here's where all this becomes key to how to solve all this, is these little squares, the relationship squares. So what this tells us is that if the temperature increases, it is going to be warmer if touched, that's guaranteed. This is for solutions. So this is relationship squares of solutions. That means chemical and water. That's the hardest ones. It's going to be warmer if touched. It's going to be exothermic. Why? Because if the water is warmer, it's gaining energy from something. And what is it gaining energy from? The chemical. So from the chemical's point of view, which is our system, it's exothermic. So your Q is going to be negative. And as a result of that, your temperature increases. So these are all connected. If one of these is true for a solution, all of these are true for a solution. Very important to remember that. So if one of these is true for a solution, all of them are true. So as soon as you know the temperature increases, you can say, okay, it's warmer of touch, it's exothermic, it's negative Q. Guaranteed. You don't have to do any additional analysis. Same way, if it's endothermic, it's going to be colder of touch, so the temperature decreases. So whenever you see a reaction where temperature goes down, it's endothermic. It's going to be colder when you touch it, and your Q is going to be positive. These are all guaranteed. If one of these is happening, all of them are happening. So if you notice the solutions, Q is positive, then that means it's endothermic, colder of touch, and temperature decreases. That's the relationship you have to figure out really quickly. All right, energy and chemical reactions. So some general state changes, just to make you aware of it. Freezing of water. It's exothermic. Why? You're losing energy. You're going from a liquid to a solid. That's a loss of energy. Why? What has more energy, the solid or the liquid? The liquid does. So in order to become a solid, you have to lose energy to become a solid. It moves more slowly. That's the best way to address these kind of state change questions. Ask yourself, do I have to put energy in to make it happen, or do I take energy out? For example, condensation of water. You're going from a gas to a liquid. Are you absorbing energy or are you losing energy? Losing, because gas is more energetic than a liquid. You have to make the molecules get closer together and they start interacting more. Let's look at the flip side, melting of ice. In order to melt ice, what do you have to do? Add heat, right? Because you're going from a solid to a liquid. So you're adding heat to make this happen. As a result of that, this is endothermic. Evaporation of water, which is going from liquid to gas. You're again adding heat. And these are all the examples of endothermic and exothermic reactions. So once again, the question is, are you absorbing energy? Are you releasing energy? And remember, this is all from the point of the system. That's the most important thing. So if it's water by itself, water is the system. If it's a metal by itself, metal is the system. If you have a chemical in water, then the chemical is the system. And that's the hardest ones, right? Another example. So you have 80 grams of water, 80 grams of NaOH and 120 grams of water. So what's your total mass in the situation? 200 grams. You have to add the masses together, right? That's what we typically do. So we have 80 plus 120, that's 200 grams. Temperature is going from 20, that's Ti, that's Tf. So now let's go back to our square thing for solutions, right? So what do you expect to happen here? Temperature is going up. So we know for solutions that always means exothermic, right? It's always exothermic reaction. It's only for solutions, not for water by itself, not for metal by itself, for solutions. So it's exothermic, which means it's going to be warm to touch, which means your Q is going to be negative. This is what you want to do in all these questions. First, figure out this, and then before you do the numbers, you already know what's supposed to happen. So when you do your numbers, you'll be able to support your argument. So Q equals MCAT, so 200 times 4.18 times 20 gives us 16,720 joules. This is the key of the water, not the chemical. Remember, we've got to flip the sign, and voila, negative the number. Checks out. We expect to be exothermic, it is. We expect to be negative, it is. So if I were to touch this item, it'd be warm, exactly as we expect it to be. Very important you get in the habit of doing those in that sequence to make sure you figure out what's going on before you do the math. All right, so our last few questions. Explain if the reaction is exothermic or endothermic. Cup of coffee left outside on a cool day. You expect the coffee to be warmer than the outside, so it's going to be losing energy, so that's exothermic. Just remember, exo is negative. Losing is bad. Losing is negative, and that's the easy way to look at it. You add ice to your soda. Soda is the system. So from point of the from the soda, it's losing energy to get colder, right? Anytime you lose, that's exothermic. You jump in a pool on a hot day, you are the system. Once again, look at it from your point of view. So you are losing energy to the pool. That's why you're not as hot, right? That's why you jump in the pool to begin with. So that's exothermic again. 4, a boy burns his hand on the stove. In order to burn his hand, he has to be absorbing energy from the stove. That's endothermic. 5, an aerosol can left outside on a hot day explodes. It's absorbing energy. That's why it's exploding. So the absorbing energy is endothermic, but the explosion is exothermic. So it's actually both occurring simultaneously. And the last one, you put an ice pack on your knee, you are the system. Why are you putting an ice pack? Because you are in pain, and what does the ice do? It makes you feel cooler, right? And start desensitizing the pain. So you're losing energy to the ice pack. So that's once again going to be exothermic.